Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. So far in this playlist, we've only been looking at Galois theory in the context of finite field extensions. In this video, I want to show you how we can look at infinite field extensions and apply Galois theory there by taking limits of finite field extensions. And the key to this is a small addendum to the Galois correspondence. Okay, so remember roughly the Galois correspondence, what is it talking about? It's a situation where you have some sort of finite Galois extension, say K over F, say with Galois group G, and the correspondence is between intermediate fields of K over F, so intermediate fields L like this one here, and subgroups of this G. So this will be finite, so it has a finite degree, and that degree equals the order of this finite group G. So there's certainly a finite number of elements on this side here. Okay, so what does this addendum say? This addendum is talking about a sub relationship here. So instead of looking at all the subgroups here, we just want to look at the normal subgroups. The normal subgroups there, do they correspond to special intermediate fields on this side? And the answer is yes. So which ones do they correspond to? Okay, so if you have a normal subgroup n inside G, okay, so what's the corresponding intermediate field? Of course, that's given by the fixed field of n, so all the elements inside K, which are fixed by all the group elements inside n. They're the ones that such that L over F is Galois. So note that K is still Galois over L, but it's not necessarily true that L is Galois over F. And to see when this is actually Galois, you can test it on the group theory side by just checking to see whether the corresponding group is normal or not. So that's a very, very nice criterion. So in this case, you can say even more. So one of the natural questions is that, well, if this is Galois, then we want to know what is the Galois group of L over F. A very, very natural question. So this is the little result that we have. That's very important for us. Okay, so this is the addendum to the Galois correspondence. Okay, so not only do we have this correspondence restricts, okay, on this level of normal subgroups to the intermediate fields such that L over F is Galois, you have more information about the Galois group of this L over F as well. So in fact, there's a surjective homomorphism from the Galois group of K over F, the big Galois group, to this Galois group of L over F. Okay, so how does that work? So it's quite simple. What you can do is you can take an element inside there, phi, and then what you can do is you can just restrict this element of G. Okay, so that's an automorphism of the field K, which fixes all of F, and we're just going to restrict it to L. And the point is that this will restrict to an automorphism of L, and of course it still fixes F, and of course since we're just restricting, this is still a ring homomorphism, okay, and of course the multiplication is the same, it's just composition of automorphism, so this will be a ring, a group homomorphism, okay. So the only thing actually you have to check is that this is well defined, okay, so this restricts to an automorphism of L, okay. So that's the most important thing. So this is a homomorphism, and in fact it's also surjective. Okay, so once it's surjective, actually that tells you a lot of information about this, because you can apply the first isomorphism theorem from group theory to say that this is just then isomorphic to the Galois group of K over F, so this G, so this Galois group of L over F is just isomorphic to G over the kernel of this map. And the kernel of this map is just N. Okay, so that's the corresponding group to L. So this is G mod N. So this is a really, really nice result. Okay, so if you look at this, what can you do with this group? You can look at subgroups, and they give you the intermediate fields. You can look at normal subgroups and then the corresponding quotients. And what do those quotients correspond to? Those quotients correspond to the intermediate fields, such that this is Galois and it's their Galois groups. Okay, so this is a really, really nice result. Okay, I don't want to go through the proof of this addendum. There's quite a bit in there, but let me just state roughly why this is true. So remember, if L over F is Galois, okay, so what you have there, so you basically have a splitting field. Okay, so L is a splitting field over F, so it's a splitting field of some polynomial. And what does an element phi inside here? a Galois automorphism do to that? Well, it has to just permute the roots of those that polynomial, okay? And since it's just permuting the roots of those polynomials, that means that the field generated by those roots, which is just L, has to stay fixed, okay? So it has to, phi of L is inside L. And of course, you can apply this argument to phi inverse to show that phi inverse of L is inside L. So actually, this phi restricts to an automorphism of L. Okay, so let me just briefly explain to you why the rest of in this direction is true. Okay, so why if you have a Galois extension L over F like this, you get these results. So the first thing is surjectivity of this homomorphism. Okay, so this basically corresponds to the uniqueness of splitting field. So K is the splitting field over F. So if you have a Galois automorphism from L to F here, okay, then K is still a splitting field of over L. So you can lift that using the uniqueness of this splitting field K. You can lift that automorphism to 1 here. Okay, so that's one of the interesting things that you can do with uniqueness of splitting fields. Okay, so that's surjectivity. And the last thing is just to see, well, what is the kernel of this? And that's actually quite easy to see, because the kernel of this is precisely, okay, all the automorphisms here, okay, all the Galois automorphisms, such that when you restrict them to L, you're going to get the trivial automorphism. Okay, so in other words, it's trivial on L. So all the things which are trivial on L, of course, that's going to be, since N is the thing corresponding to this fixed field here, okay, of course, N fixes all of L, and that's the corresponding group that you have here. Okay, so that's why the kernel of pi is equal to N. And this gives this lovely result. Okay, so let's now turn our attention to infinite extensions. So suppose we have a field extension K over F, which is possibly infinite. Okay, when do we say that's Galois? So we say it's Galois if it's a splitting field of now not just one separable polynomial, but a whole family of separable polynomials f alpha inside f of x. Okay, so that means that this is just some collection, possibly infinite, of polynomials, okay, in f of x. Each of them is separable, and to be the splitting field of this means that in K, all of these polynomials will factor over K into linears. Okay, so it certainly splits. And it's the smallest such field in the sense that it's generated by the roots of all of these polynomials. Okay, so that's the definition of Galois in this infinite case. So note that with this infinite extension here, it's still generated by roots of polynomials, and hence it's still an algebraic extension. Okay, so Galois theory doesn't look at the case where you have transcendental extensions. It's still an algebraic extension. Okay, so what we're going to do here to study this is we're going to use finite Galois theory. So what we're going to do is we're going to look at all the subfields of K containing F, so all the intermediate fields which are Galois. Okay, so we look at all the K alpha which contain F, okay, intermediate extensions K alpha, which are Galois sub-extensions, so to be. Okay, so look at those K alpha, which are Galois, and we're going to consider this as a poset. Okay, so these are all subsets of K, so you can order them by inclusion. So that's a poset. Okay, and so remember, when we want to take inverse limits of groups, we need a poset. So that's the reason why we're going to introduce that. Okay, so the first point to note is that this K, it's in a sense a limit of these K alphas. Okay, so in what sense is it a limit? Well, K is just equal to the union of these K alphas. So we should be able to understand K by looking at all the K alphas in totality. Okay, so that's the idea behind how we want to study K using Galois theory, by using the Galois theory of each and every single one of these K alphas over F. Okay, and this is quite easy to see why it's true, because remember K over F, it's going to be assumed Galois, okay, and that means that it's generated by the root of these polynomials, and so any particular element inside here, okay, you can express some sort of rational operation in some finite set of these roots. Okay, and those finite set of roots must be roots of a finite set of these polynomials, so you can multiply all those polynomials together, and the splitting field of that product of polynomials, of course, is going to contain that element. Okay, so that's why this result holds true. Okay, now what we want to do is we want to apply Galois theory to each of these, and what I want to do is to get an inverse system of groups. Okay, so how am I going to do that? So firstly, for each of these k alphas over f, okay, we have a Galois group G alpha. That's the first point. And then the next thing that we need to get an inverse system of groups is we need to relate all these Galois groups to each other. Okay, and the situation we want to relate them is when some k alpha is contained inside some k beta. Okay, so when that happens, what we want to do is we want to have a map from this Galois group G beta to the Galois group G alpha. And what's that going to be? It's quite easy to define. Okay, so suppose we have some element of G beta. So that's some automorphism of k beta fixing f, and we just restrict it to k alpha. And since k alpha over f is Galois, we can use this addendum to get that map. Okay, so this is just phi restricted to k alpha. Okay, and it's quite easy to see that since we're just restricting maps here, okay, that this actually gives an inverse system of groups. So on the field side, we take off what's called the direct limit, which in this case is just simply union of these fields. And the Galois theory side, where we have this correspondence, which reverses inclusions, okay, so it's in the inverse direction, we have this inverse system of groups, so we can take the direct limit, the inverse limit of that, and we call that G hat. Okay. And the theorem is as follows. Okay. The theorem is wonderful. In this case here, we can say precisely what the Galois group of k over f is in terms of these, this inverse system of groups. In fact, it's just isomorphic to G hat. Okay, so that's the first point. And the second point is that you also get a Galois correspondence, okay, but it's a little bit more subtle this time. So what you have here is that on one hand you have intermediate fields, okay, L, sandwiched between f and k. And now when you look at subgroups of this Galois group, which is G hat, you can't look at all of them. So you have to look at only the closed subgroups. So remember this G hat, it's a profinite group, so it has a topology. Okay, and so we can talk about the closed subgroups of that. Okay, so let me just add some more details as to how this works. So firstly, how do we get this isomorphism? So here what we can do is that we can take a Galois automorphism inside here, and to map it to this inverse limit. Remember, this inverse limit is a tuple. Okay, it's a tuple of elements, one in each of these G alphas. Okay, and they have to be compatible. And so what is that? So basically using the argument here, what happens is that this is a Galois automorphism. Okay, then it has to be to restrict to an automorphism of k alpha, which of course fixes f. So we can restrict this phi to k alpha, and we look at this tuple for all alpha. Okay, for all of these finite Galois subextensions. Okay, and clearly it's going to satisfy the compatibility condition to land inside this G hat. And in fact, this is going to be an isomorphism. And it's not too difficult to show that this is actually an isomorphism, okay, if you understand the finite Galois theory well enough, and also you understand the universal property of inverse limits. Okay, so how does the bijective correspondence work? It works in exactly the same way. If you're given an intermediate field, okay, L, to get the other side, what you can do is you can look at the Galois group of k over L. Okay, so remember this is always a Galois, and there's the Galois group of that. And here H, given a closed subgroup, you can look at the fixed field here. Now note that you can apply this map even if the group is not closed, but then you get many more elements here, And so this is no longer a correspondence, a one-to-one correspondence. And to see that, we have a little example. Okay, so let's look at this example here. Here we're going to fix some prime, and we could look at the finite field Fp. And then we'll consider the following Galois extension, which is the algebraic closure of Fp. So we know that what this essentially is, this algebraic closure. You can get this just by taking the union of all the finite fields of characteristic P, and each of them is a separable extension. Okay, so that's why it is just this. It is Galois, just a splitting field of some family of separable polynomials. Okay, and you can write down that family of separable polynomials quite easily as well. Okay, so what is this? So firstly, one thing that we have here is that we have the Frobenius automorphism. Because this is characteristic P, there's a Frobenius automorphism on this Fp bar. And we can also write this Fp bar as a union of all the finite fields. And the Galois group of finite field over Fp is some cyclic group generated by the Frobenius. So when you take the inverse limit of that, we've seen that that inverse limit is just going to be z hat. Okay. So what this will turn out to be is it's actually just the closure of the subgroup generated by the Frobenius. Okay, so that's the Galois group of this infinite Galois extension. It's z hat, and it's topologically generated by the Frobenius map. So note that, of course, if you start with this big field, okay, and you start with this subgroup generated by the Frobenius, so this infinite cyclic group generated by Frobenius, you can apply this map over here, and you'll get Fp. But this is not this cyclic group is not the one corresponding to Fp. The one corresponding to Fp has to be a closed subgroup. So we actually have to take the closure of this group to get the one corresponding to Fp. Okay, so of course, if you look at what's the fixed points of this closed subgroup, of course, that's the whole Galois group. So you will get Fp in that case. So if you want one-to-one correspondence, okay, you've got to restrict yourself just to closed subgroups. Otherwise, there are many more over here. Okay, and yeah, so going this direction, you'll only hit this closed subgroups, and some non-closed subgroups will give you the same image as a closed subgroup in this way. Okay, so let's have a look at some other interesting features of this field extension here. So I'm going to try to build for you an intermediate field, okay? And the way I'll do this is I'll fix L is going to be a prime. And if you have a prime, well, of course, we can start with Fp, and we can get a bigger field, which is Fp to the L. Okay, so that's a degree L extension. And then we can take a degree L extension of that, which will be Fpl squared. And then we can keep going to higher and higher powers of L here. And we let Fpl to the infinity be the union of all of these. Okay, so each of these is a separable field extension. So you get it by adjoining the roots of a separable polynomial. And so the union of this also will be a Galois extension. Okay, and of course this is inside the algebraic closure of Fp. Okay, so it is Galois sub-extension of that. And so that gives you an interesting intermediate field. So let's just see what's going on with this interesting intermediate field. Okay. So the first thing is that so Fp bar over Fp, we have this field extension here, and this is going to be a Galois sub-extension. So using the same argument as we have in this addendum here, we can restrict Galois automorphisms here to Galois automorphisms of this Fpl to the infinity. Okay, so that's just restriction. Okay. So that's phi here gets mapped to phi restricted to F Pl infinity. Okay, so that's all very well and good. And also this is going to be surjective. It's a surjective map. Okay, so what was this Galois group? Remember this Galois group here is just that z hat. And that equals, just to remind you, it's the limit of all the z mod n, the inverse limit of all the z mod n. Well, what about this one here? What is this Galois group? So this Galois group is also a limit. We can look at this union here. And it's the limit of all z mod L to the n. So the Galois group of the nth one here, this over this, okay, is z mod L. The Galois group of this over this is z mod L squared. Remember, they're all cyclic, and the degree of this extension is L squared, so it's z mod L squared. And then have z mod L cubed. And so this is just, remember, is just z hat L. So it turns out there's a surjective map from here to here. And how does that work? So basically what you have here is for each n, this is a tuple, one for each n. And for each n, you just have some sort of coset of n. Say it's given by alpha n. And this maps to, well, for each n here, you have a coset of L to the n. And it's just that corresponding one here. So in other words, this is a tuple over all the positive integers. And what you do is you just pick out the ones correspond to an index, which is a power of L. That's all this does. And that's the surjective map. So interestingly enough, you have this surjection from here to here. And in fact, this splits. So the kernel of this, okay, is going to give you the group corresponding to this subextension in the Galois correspondence. But it also tells you, it gives you a way of viewing, okay, what this group looks like. Okay, so this group has as a factor z hat L for any prime, and essentially it's just the product of those. So that's how you get this z hat. Okay, so let me just finish off with this last definition, which is going to be important when we try to think about Galois theory from a more sophisticated point of view. Okay, so suppose you're given a field F. Okay. What do we like to do is we like to look at something called the separable closure of F. So F sep, that's the splitting field of the collection of all possible separable polynomials over F. Okay, that's called the separable closure, so we denote it as F sep. So if you're in characteristic 0, this is just the algebraic closure. It's not really a new sort of concept. And then what we're going to do is we're going to define the absolute Galois group of F to be just the Galois group of F sep over F. Okay, so normally when you use Galois theory, it's a relative concept. You look at a field extension, right? Okay, one field over another, and you study that field extension. Okay, so but often what you want to do is you want to just study a field in itself. Okay, so how to use Galois theory? Well, it turns out that the way you do that is that you look at the Galois theory essentially of all Galois extensions of that, and that basically gives you this separable splitting field. Okay, this separable closure. Okay, so you look at that. So you look at that, and that allows you to study a field. Okay, and the point of this is that in many ways, this absolute Galois group, you should think of this as the arithmetic analog of the fundamental group that you see in topology. And this separable closure, okay, so what's that corresponding to? The separable closure you can view as an analog of the universal or the simply connected cover of a topological space. And so this is a very, very important concept. And when we talk about infinite Galois theory, often this is the setting that we want to look at. I hope you enjoyed this adventure in pure mathematics.